Last time we saw the quantifiers for all and their exist. Today we'll see how to use them in order to write down proofs. If we have a statement of the form for every number x something holds, the structure of the proof will be let x be a number, and then we'll show for general x, which we did not assume anything on it except of being a number, we'll prove the general statement. If we have an existent statement, such as there exists, sorry, I don't have S in this slideshow, there exists a number x, then the proof should begin with showing this x. If I show there exists a black cat, I show you a black cat, I proved that there exists a black cat. Now let's see how to use what we learned now and what we learned in the video of negation of statements in order to prove or disprove several statements. We begin with the statement number 1. If r is irrational, then r squared is irrational. So first of all, we ask ourselves if this is true or false. False. Intuitively, it is false. Why, if something is irrational, its square should also be irrational? We don't think it makes sense. But now we want to translate the if-then form to a form of quantifiers. When we state a statement of if something, then something else, actually we say that for all something else holds. Or in our example, we say that for all irrational r squared is irrational. And this is false. How we show it is false? A statement of for all we prove generally, but in order to disprove it, we need to negate it and then prove the negation. The negation of a general statement is an existence statement. There exists R in Q such that R squared is not R minus Q such that R squared is not in R minus Q. In our question, this r in r minus q that we take as an example is square root of 2. Square root of 2 is irrational, but square root of 2 is 2, which is rational. Why we call it a counterexample? It is just an example. We call it a counterexample when the example uses us to disprove something. Now to the next example. The statement is, if Q is rational and R is irrational, then the multiplication is irrational. This statement is also a general statement. For all Q in Q and R in R minus Q, R times Q is in R minus Q. And this is also false. Since this is a general statement, in order to prove it is false, we need to give an example for a number that is rational and another number that is irrational and show the multiplication is rational and not as said here, irrational. Our example will be 0 and square root of 2. The multiplication of them is rational, 0. Now to the next example and last for today. We take R to be a positive number and irrational, and n is a natural number. We state here that n is greater than 1, so that it is a natural number from 2 and on, 2, 3, and so on. And the statement says that the nth root of r is irrational. This statement actually says that for all positive r and for all greater than 1 n, the nth root of r is irrational. Actually, this statement is true. And in order to prove it, if we want to prove a general statement, we usually will say, let R be an irrational number and let N be a natural number, and then just show it holds. But since the statement is that something is irrational and we don't have a classification of what does it mean being an irrational number, usually when we want to prove the final statement of being irrational, as we did in the proof of square root of 2 being irrational, we will use proof by contradiction. which means we actually, instead of proving that the left side implies the right side, we prove that if we assume the left side and the negation of the right side, then we get a contradiction. So let's assume towards a contradiction that the nth root of r is a rational number, which we know is not, but we assume now it is in order to get a contradiction. Then, if we raise nth root of r to the power of n, which means we multiply nth root of r n times by itself, we get r, which we assumed to be irrational. But now we get that it is irrational since this is a multiplication of n rational numbers, or n times a rational number by itself. Therefore, we get a contradiction. So our assumption that nth root of r is not a rational number, that it is a rational number, our assumption was wrong, and therefore r is not a rational number. Therefore, the nth root of r is not a rational number.